So here's a second order linear constant coefficient, non-homogeneous, because of this piece, differential equation. So we know in order to solve this, we want to get a homogeneous solution first and then get a particular solution. Then the general solution or the complete solution is the homogeneous solution plus the particular solution. And at the end, after we've got the general solution, then if they give us any initial conditions, we can find the constants. That's the last thing we do. There's no initial conditions given in this example, so we don't have to find the C's. All right, so step one is get the homogeneous solution. So in other words, solve this. Homogeneous, we replace this piece with 0. We've got our auxiliary equation, prime prime becomes lambda squared, 1 prime becomes 1 lambda, no prime becomes no lambda. Solve for the eigenvalue, solve for lambda, and I get a complex conjugate pair of eigenvalues. So lambda equals 1 plus or minus 2i. I would have done the quadratic equation on that. Pause the video, do the quadratic equation, you should get those answers. That means my two little solutions are e to the real part t, so e to the 1t, times sine imaginary part t, and then e to the real part t cos imaginary part t. So the imaginary part goes in the trig, the real part goes on the e part, and both of them have a t. There's a t on the top and there's a t inside the trig. So there's our homogeneous solution. C1 y1 plus C2 y2. We've got our homogeneous solution. Next step, get the particular solution. So we know two different ways of getting the particular solution. Unknown coefficients is an idea, but it's a bad idea for this one because there's no good guess that'll give us this secant. We have to go with variation of parameters. Unknown coefficients won't work. I have the y1 and y2, so I'm getting ready to do variation of parameters. I need y1 prime, so I've just differentiated it. Product rule because it's a function times a function. I've got y2, which is the other little solution. The y1s and y2s, where are they coming from? They come from the eigenvalues. Those are the pieces of the homogeneous solution that we add together in a linear combination to get the homogeneous solution. So we've got our y1 and y2, our y1 prime and y2 prime. The Wronskian is a piece of the formula, so let's get the Wronskian. The Wronskian is y1 times y2 minus y2 times y1 prime. So I've got y1 times y2 prime minus y2 times y1 prime. And when we simplify that all up, use the sine squared plus cos squared equals 1 identity, we end up getting a Wronskian of minus 2 e to the 2t. So we need our pieces for our variation of parameters formula. So let's go focus on what we're doing here. We're trying to get a particular solution to that differential equation. Our particular solution then it will be of the form v1y1 plus v2y2. We already have the y1s and y2s. We already have our y1. That would be this piece here. Our y2, that would be this piece here. If your y1 is my y2, it won't matter. The math will switch the v1 and v2 around. So we'll get the same answer. So we already have the y1 and y2. We just need the v's. The v's have the formula v1 is equal to integrate minus gy2 over a times the Wronskian. The v1 has the minus, so let's get that. Minus the g is the target function. The g is the non-homogeneous part. So in our case, the g is the e to the t secant 2t. The v1 has the y2 in it, so I'm multiplying by the y2. And then we're dividing by a times the Wronskian. The a is the coefficient in front of the y prime prime. In that case, that's just 1, so I won't write it. The Wronskian is our minus 2 e to the 2t. We already built that. And now I just have to do that integration. Now sometimes that integration is hard, but in this case, it's actually not going to be too bad because this e to the 2t cancels off with this e to the t and this e to the t. That minus on the top cancels with that minus on the bottom. Secant is 1 over cosine, So the secant and the cosine cancel. We're actually just integrating a half. When all that simplifies down, we're integrating a half with respect to t, and that's just t over 2, or 1/2 t. Don't need the constants in this case. So that first integration, pretty straightforward. The second integration for v2 is going to equal to g, the target function. So no minus in the v2 piece. There is a minus in the v1 piece. So g times y1, so our y1 is e to the 2, all divided by a, which is 1, times the Wronskian. So now I have to do this integration. This one doesn't simplify down as much, but let's see what we do get. The e to the 2t cancels off the e to the t, because e to the t times e to the t, add the exponents, would be e to the 2t, and then the e to the 2t's would cancel. The secant is 1 over cos, so secant times sine, or 1 over cos times sine, that's sine over cos, that should simplify down to be tan. So we just have to integrate tan. Let's bring that minus a half to the outside, and we just need to know our integral of tan 2x. Now the integral of tan, let's move ourselves down here. The integral of tan is going to be, so I have to integrate, and now I've got v2. So our particular solution is going to be v1, so our v1 is just this t over 2, times y1, and v2 is, so I've got my v1, y1, v2, y2. It looks messy, but this is the particular solution. So that means the general solution is our actual complete solution. That means the general solution is going to be equal to the homogeneous solution, which we had all the way up here, plus the particular solution. This is our complete solution. That's the answer to the differential equation. We can see the particular solution, we can see the homogeneous solution. It's at this stage that if they gave me initial conditions, this is the place where I would sub in and solve for the C1 and C2.